All right, so as I said at the end of that last video, we can determine the long-run behavior of a rational function just by looking at the leading term of the polynomial in the numerator and the leading term in the polynomial in the denominator. All right, so remember the leading term is the term with the highest power of x. Okay, and so we can look at the behavior of that ratio. So it just becomes the ratio of two power functions, and we can then that gives us the behavior of the whole polynomial. Okay, because those leading terms are going to dominate in the long run over any other powers of x. All right, so and if that limit is finite, then we have a horizontal asymptote. So in this next example, we're going to look at some polynomials. We're going to look at find the long run behavior, and then we're going to give the equation of any horizontal asymptotes. So, all right, so let's take a look at this first one. We have the polynomial 2x minus 1 over x plus 2. So remember, okay, so we're going to start by looking at, we're just going to say as x goes to plus or minus infinity, right? That's how we determine long run behavior. We look at what happens as x gets really, really large in the positive direction or goes farther and farther negative. All right, so we're going to say that this f of x, as x gets larger and larger in either the positive or negative direction, we're just going to look at the leading term of the numerators, which is just going to be 2x. The highest power of x is x to the 1, right? Because this is x to the 1. X is just x to the 1. And the leading term of the denominator is just x. Okay, again, x to the 1. All right. Now you look at that ratio, and that ratio, those x's would cancel as long as x is not 0, right? So it seems that that goes to 2. All right. So now we can express the long run behavior as the limit as x goes to, and I'm going to just go ahead and, because it goes to the same value whether we go to in the positive or negative direction. So I'm going to just express both limits as in 1. All right, just because they have the same limit of f of x. So I'm going to say as x goes to either plus or minus infinity, the limit is 2, and so we have a horizontal asymptote. So horizontal asymptote at and the equation is going to be a y equals 2. Okay, so horizontal asymptotes are always y equals something because the y value is constant all along that line. All right, so let's look at this one as well. So as x goes to either plus or minus infinity, we're going to look at g of x, and we're just going to look at the leading terms in the numerator. Whoops, that's a 3. 3x, right? That's the leading term in the numerator, and then x squared is the leading term, the highest power of x. Now, if we cancel an x, this becomes 3 over x. Okay, so what happens to 3 over x as x gets larger and larger and larger and larger? In the positive direction, we're just dividing 3 into, more and more and more pieces, essentially. And so it's going to go to 0. And it'll do that in either either when x goes to positive infinity or negative infinity. Okay, it's going to go to 0. And so we can express the long run behavior in limit notation by x goes to plus or minus infinity of g of x is equal to 0, and we're going to have an asymptote. Horizontal asymptote at y equals 0. Okay, which y equals 0 is the x-axis. All right, so let's look at the next one. Here we have, we're going to again do the same thing. We're going to look at what happens as x goes to plus or minus infinity. All right, and we're just going to look at the ratio of the leading terms in the numerator and denominator. So we have x to the 5th as the highest power of x in the numerator, and the highest power of x in the denominator is x to the 4th. Now, if I reduce that, just becomes x. All right, so what happens as x goes to positive infinity? If x goes to positive infinity, then h of x goes to positive infinity. If it goes to negative infinity, though, it goes to negative infinity, right? So it just follows whatever happens to x. So in this case, I can't just express the long-run behavior in limit notation with one limit. So I have to break it up into two different limits if they're going to two different things, right? So as x goes to positive infinity, h of x goes to positive infinity. And if x goes to negative infinity, h of x goes to negative infinity. All right. So we don't have a finite limit, so there's no horizontal asymptote. So I don't have to worry about writing the formula for it. So it just goes to positive infinity or negative infinity, and there's no asymptote. All right, this last one is a little bit, it's not written as a rational function right now. It's the sum of two rational functions, but we can rewrite this, right? I need a common denominator, so I'm going to take the first ratio, and it's missing a factor of x minus 3 in its denominator. So I'm going to multiply it by x minus 3 over x minus 3. Okay, so I haven't changed anything because I'm just multiplying by 1. Now the second fraction is missing an x plus 1, a factor of x plus 1, so I'm going to multiply by x plus 1, x plus 1 over x plus 1, and then so again x plus 1 times x minus 3 in the denominator. So now I have a common denominator, and I have to multiply this out. I'm going to multiply the numerator out, so I'm going to get 3x squared minus 9x. So since I have a common denominator, I can just add the numerators, right? So I'm going to end up with a plus x and the plus 1. All right, and then I'm going to multiply out this denominator because I need to compare the leading terms. So when I multiply that out, I would get x squared, and then I get x minus 3x. So that's going to be a minus 2x and then minus 3. All right, so now I have the numerator and denominator expressed as polynomials, and I can see what the leading terms are. Now I could simplify this a little more because I have a minus 9x and a plus an x, but I don't really care about that because I only care about the leading terms when I look at the long run behavior, right? So I'm going to look at as x goes to plus or minus infinity. Now we have this k of x it goes to 3x squared over x squared, which is 3. So I can say that the limit as x approaches plus or minus infinity, so I can write this as one limit, and the function is k of x. I could write out the whole polynomial or the whole function, but it's just easier to write k of x. And then so the limit is 3, and since it is a finite number, then I can say that there's a horizontal asymptote. Need an abbreviation for that. At y equals 3. All right. So I will meet you in the next video for the next example.